Okay, so welcome back now. We were talking about processors. This is where the central part of the computer is manipulating. One part is the control unit. These are the instructions, and the arithmetic unit, and it's pulling information instructions in and out of memory in the process. So there are really two types of processors. AMD and Intel. Intel Inside is a common commercial theme. So overall, both companies produce processors that frankly are within striking distance of one another on nearly every front: price, power, performance. Intel chips, for example, tend to offer a little better performance in their core, but AMD compensates with more cores at a given price and better onboard graphics, etc. So just a little bit about the two main competitors for processors. Now, a CPU cooler is a device designed to draw heat away from the system CPU and other components in the enclosure. So using a CPU cooler to lower the CPU temperatures, it's going to improve the efficiency and stability of the system. So adding a cooler device, however, you should note, can increase the overall noise level of the system if that's a concern for you. So there's such a thing as a heat sink. Heat sink is a small ceramic or metal component with fins on the surface, and it absorbs and disperses heat produced by these electrical components, such as the processor. Liquid cooling is a type of technology that uses continuous flow of fluid or fluids, as such as water or glycol in the process, and it's going to transfer the heated fluid away from the processor. And then, of course, you could have a cooling pad, just a basic pad, that rests below the laptop. It's going to do a couple of things. It's going to protect the computer from overheating, and also it's going to protect your lap from excessive heat. So the heat sink, as I said, is a piece of metal that sits on top of the computer chip, such as a CPU, and it's going to draw that power away from components by letting it rise through a set of fins. So by themselves, heat sinks are just passive. They have no real moving parts. And so you might ask, well, do I need a heat sink? Well, the answer would be yes. You have to have a CPU heat sink, even if you are not overclocking the CPU, or the CPU will burn up. If you're not overclocking, you can use a typical heat sink, and you'll be fine. It doesn't have to be anything special. But if you're getting a high-powered CPU that didn't come with a heat sink, you'd have to buy one. You really would. So really, the overclocking is beyond this course, but I'll just touch on it quickly. So to speed up a computer beyond the manufacturer's specs, in order to make it run faster, this is common in the gaming world, right? Some people will overclock the CPU, and this is accomplished by changing the clock ratio on the front side bus in the BIOS setup. Again, beyond this course, don't worry about it really. Just for those that are interested in gaming may enjoy that. So now processors, continuing with that topic. A laptop or notebook cooler, or sometimes called a cooler pad or a chill mat. Again, I was just talking about this on the last slide too, but it's an accessory for the laptop computers that helps reduce that operating temperature and is normally used when the laptop is unable to sufficiently cool itself, right? The pad may house some active or passive cooling. There are various types out there, depending on your needs. Now, moving from CPUs and cloud computing, I'd like to begin to touch on CPUs and cooling, rather. I'd like to move to cloud computing. So recall that cloud computing allows access to resources that for users through the use of the internet, right? It provides us, we know, this accessibility and some cost savings because they don't have to buy extra storage devices for my house or my work. I can use the cloud. So it's going to provide also space savings and scalability. If I need to expand rapidly, I can just request more cloud space. But if I'm not using it, I can decrease that and cut my costs. So cloud computing consists of a front end and a back end, and connected to each is this network. We're connecting to the back end of the front end, like your computer through the network to the cloud, or the cloud through your network to your computer, back end and a front end. Now, I did want to touch on types of cloud computing. Cloud computing, again, implies this sort of virtualization. It's not really on our premises. And this is going to provide, I mentioned, that rapid elasticity of IT services, right? Or I mentioned the term scalability, right? This elasticity, I can expand and contract quickly. So just be aware there are several types of cloud computing. One is PaaS. That's platform as a service, which is going to provide IT services over a network, such as it's going to provide you virtual servers, databases, and APIs, which is that integration between systems to make sure that they can talk to each other. Now, a SaaS, or software as a service, enables productivity, right? So it's going to have, and I show some examples there. Gmail, Salesforce, ServiceNow is a ticketing thing, so it's for productivity. And then there's IaaS, or infrastructure as a service. This is going to be end-to-end everything. Your network, your storage, your backup services, everything in the network. It's going to provide everything, including your operating systems, right, in computing. Now, I did want to touch just quickly on virtual desktops. Virtual desktops are a virtual desktop environment known as VDE. It's going to maintain everything related to your desktop. So you're looking at your desktop or your laptop right now. And that can be created in a virtual environment and deployed to a host somewhere. And so this virtual desktop infrastructure can make our desktops more secure, potentially, right? So I can store data on VDI servers in the data center, which is more secure than storing them on local machines, right? And also, administrators now can have greater access, greater control over the desktop and the application distribution through this virtual environment, right? I've defined what a user should get on their desktop, and that's all they're going to get through this virtual environment. And I even have some protection accomplished through sandboxing, again, beyond this course, but interesting, right? So be aware of that. And then the last term I wanted to mention in terms of cloud computing here is about mashups, right? So mashup is a creative way of putting things together, right? So like in songs, right, a mashup is created by blending two or more pre-recorded songs together, kind of superimposing them in a vocal track into the seamless sort of instrumental track, and reducing gaps, etc. Well, in computer terms, mashups are applications that are going to incorporate data from multiple providers into a new application. So, for example, I might display homes in a neighborhood with crime statistics and then on top of a map. Those three data sources would be the example of a mashup, right, of this data from real estate and police records and mapping providers. Okay. Now, continuing beyond the CPU and the cloud, now we want to talk about how the data is represented. So human speech is analog. It's analog because it's a continuous waveform of signals. Most computers, though, are digital. Humans are analog, computers are digital. Digital means they only recognize on and off. Two digits, a 0 and a 1. 0 represents off and 1 represents on. So actually there's no big difference between, it's not a major difference between the 1 and 0, on and off. And it's translated into bits. Bits are on or off, right? A number of bits would be called a byte, right? So a byte is much bigger than a bit. In fact, it's 8 times bigger to be exact, with 8 bits in every byte, B-Y-T-E. So, why do we use bits? Well, we use bits to measure the internet speed, to measure the transfer of data, etc., and to name things, right? It's essentially a single binary point, one binary point, yes or no, up or down. And so a byte, on the other hand, is a unit of memory that contains 8 bits. And this 8 bits are then used to encode a character. So I can create a code of characters in these 8 bits. So you see the ones on the screen, 1, 1, 1, 1, 1, 8 ones across, right? That is going to equal 255 potential bits on and off switches. And I can translate that into a code called ASCII, which we'll talk about in a few minutes. So I'm going to take these electronic on and off, and it's going to translate that through ASCII into some computer speak. So this is how data then is represented in a computer, on or off, right? So data representation refers to the form in which the data is stored, processed, and transmitted. Smartphones, iPods, computers, they all store data in digital formats that can be handled by electronic circuitry. And electronic circuitry handles data in terms of bits, on or off. So this next slide is meant to show you. The letter E, for example, we would take these 8 bits, which we call a byte, right? And 0, 1, 0, 0, 0, 1, 0, 1 is the letter E. And then we have, for the symbol asterisk, they show you the 8-bit byte. And then for the number 6, right? So we're translating these on and off electronic impulses into code for us. And so these are defined by patterns called coding schemes. And the coding scheme maps a set of alphanumeric characters and special symbols, numbers and letters. And ASCII, which is the American Standard Code for Information Interchange, or ASCII, ASCII, this is the most widely used coding scheme. So when you press on a key on the keyboard, a chip in the keyboard converts the key's electronic signal into a special code called a scan code. And that scan code is sent to the electronic circuitry on your motherboard. Then that electronic circuitry on your motherboard is going to, the computer is going to convert this scan code into ASCII binary form. And it's going to store it as a byte value in memory for processing. And when the processing is finished, the computer actually undoes that, and it converts the byte into human numbers, letters, special characters, and that's what we see on the computer screen. Okay, so this is a little bit about the data representation. This coding scheme is necessary because computers rely on logic, controlled by the electronic switches that know either on or off. Each of these switches, on or off, is represented by a bit whose value is 0 or 1. So coding schemes are translating these real-world data into a form that computers can easily use. So we'll take a break here, come back and talk about memory.